Module 6, Advanced Topics. NoSQL Databases. NoSQL, which stands for Not Only SQL, databases are a class of databases that do not strictly adhere to the traditional relational model used in traditional relational databases, RDBMS. NoSQL databases are designed to handle large volumes of unstructured or semi-structured data, provide high scalability and performance, and support flexible data models. There are several types of NoSQL databases, each with its own unique characteristics and use cases. Some common types of NoSQL databases are 1. Document-oriented databases. These databases store data in a semi-structured format, typically in JSON or BSON, binary JSON, format. Each document can have a varying number of fields, and the schema can be flexible, making them suitable for handling diverse data types. Examples of document-oriented databases are MongoDB, Couchbase, and RavenDB. 2. Column family stores, also known as columnar databases. These databases store data in columns instead of rows, making them highly scalable for write-heavy workloads. They are often used for time series data, logging, and analytics. Examples of column family stores are Apache Cassandra, ScyllaDB, and Google Bigtable. 3. Key-value stores. These databases store data as key-value pairs, where each data item is associated with a unique key. They are simple and highly performant and are often used for caching, session management, and high-velocity data scenarios. Examples of key-value stores are Redis, Amazon DynamoDB, and Ryac. 4. Graph databases. These databases store data in the form of graph structures, where data entities are represented as nodes and their relationships as edges. Graph databases are optimized for traversing complex relationships and are used for applications such as social networks, recommendation engines, and fraud detection. Examples of graph databases are Neo4j, Amazon Neptune, and OrientDB. 5. Time series databases. These databases are designed for handling time series data, which is typically generated in high volumes and at high velocities, such as sensor data, log data, and financial market data. They are optimized for time-based queries and data retention policies. Examples of time series databases are InfluxDB, OpenTSDB, and TimescaleDB. NoSQL databases are popular in modern applications that require handling large-scale data with high velocity, variety, and complexity, and where the flexibility of data models and high scalability are important considerations. However, they may not be suitable for all use cases, and the choice of a database type depends on the specific requirements and characteristics of the data and the application. Database integration with applications. Integration of databases with applications involves connecting and interacting with databases from within software applications to perform operations such as storing, retrieving, updating, and deleting data. This integration allows applications to leverage the power of databases to manage data effectively and efficiently. Here are some common methods for integrating databases with applications. 1. Database APIs. Many databases provide application programming interfaces, APIs, that allow applications to interact with the database programmatically. These APIs provide a set of functions or methods that applications can use to communicate with the database, execute SQL queries or other database operations, and retrieve or modify data. Examples of popular database APIs include JDBC, Java Database Connectivity, for Java applications, ADO.NET for .NET applications, and SQL Alchemy for Python applications. 2. Object Relational Mapping, ORM, frameworks. ORM frameworks provide a way to map database tables to objects in the application's programming language, making it easier to interact with the database using object-oriented programming, OOP, paradigms. ORM frameworks abstract the underlying database operations and allow developers to work with objects in their code, which are then automatically translated to database operations by the ORM framework. Examples of popular ORM frameworks include Hibernate for Java applications, Entity Framework for .NET applications, and SQL Alchemy for Python applications. 3. Database connectors or drivers. Database connectors or drivers are software components that provide a bridge between the application and the database. They enable applications to establish connections to the database, send SQL queries, and retrieve results. Database connectors or drivers are typically specific to the programming language and the database system being used. Examples include MySQL connector /J for Java applications, Scicop2 for Python applications working with PostgreSQL, and Microsoft Data.SQL client for .NET applications working with Microsoft SQL Server. 4. Query builders. Query builders are libraries or tools that provide a higher-level abstraction for building SQL queries in code. They allow developers to generate SQL queries using a more intuitive and expressive syntax compared to raw SQL, and provide additional features such as query composition, parameter binding, and query optimization. Examples of popular query builders include JPA, Java Persistence API, for Java applications, Dapper for .NET applications, and Sequelize for Node.js applications. 5. Web Service APIs. Many databases also provide web service APIs that allow applications to interact with the database over the Internet using standard web protocols such as REST, Representational State Transfer, or GraphQL. These APIs provide a way to access the database remotely, which can be useful for distributed applications or when accessing the database from different devices or platforms. Integration of databases with applications is a critical aspect of modern software development, as it enables applications to effectively manage data and interact with databases for data storage and retrieval. The choice of integration method depends on various factors such as the programming language, the type of database, the application's architecture, and the specific requirements of the application. Data warehousing and business intelligence. Data warehousing and business intelligence are closely related concepts that play a crucial role in modern businesses for data management, analysis, and decision-making. Let's explore these concepts in more detail. Data warehousing. Data warehousing refers to the process of collecting, storing, and managing large volumes of data from various sources in a centralized repository, known as a data warehouse. A data warehouse is designed to support efficient and scalable data storage and retrieval, and typically contains data from different sources such as databases, external sources, and data streams. Data warehousing involves data integration, data transformation, and data consolidation to create a unified and consistent view of data for analysis and reporting purposes. Data warehouses are optimized for performance, scalability, and data quality, and often use specialized techniques such as data indexing, partitioning, and caching to enable fast and efficient data retrieval. Data warehousing solutions also typically provide data management features such as data backup, data security, and data governance to ensure data integrity, confidentiality, and compliance with regulatory requirements. Business intelligence. Business intelligence, BI, is the process of analyzing data from various sources to derive insights and make informed decisions to support business operations, strategies, and planning. BI involves collecting, analyzing, and visualizing data to gain meaningful insights, identify trends, and uncover patterns and relationships within the data. Business intelligence tools and technologies enable organizations to explore and analyze data to gain insights that can drive better decision-making and strategic planning. Business intelligence typically involves a range of activities, such as data exploration, data visualization, ad hoc querying, and data reporting. BI tools provide interactive and user-friendly interfaces for data exploration and analysis, enabling users to create custom reports, dashboards, and visualizations to gain insights from data. BI solutions also often include features such as data integration, data modeling, and data analytics to support advanced data analysis techniques such as data mining, predictive analytics, and machine learning. Data warehousing and business intelligence are closely interconnected, as data warehousing provides the foundation for collecting, storing, and managing data for analysis, while business intelligence leverages the data in the data warehouse to gain insights and make data-driven decisions. By leveraging data warehousing and business intelligence, organizations can unlock the value of their data and make informed decisions to drive business success.
Thanks for watching. For more information, like, comment, and subscribe our channel.